Okay, let's start the lecture. So just a few things about the lab 2. So I think quite a lot of students have already done the lab 2. I reckon for the first question, because it's BUC, I think most of the questions are resolved. So one of the common patterns we see from the second question, which is the dynamic programming for the optimal binning method, is that there are a couple of things. Actually, I clarify some questions already online. One common problem, though, because we see from our side, but again, it's hard to convey the message back. But basically, in some cases, the matrix you calculate is correct. Okay, but it's really like the binning solution you give is actually incorrect. And also, I strongly encourage you guys, if you still fail some of the tests, try to test offline by yourself. For example, the matrix, right? We already give you the naive recursive definition. I mean, unless you try a very large one. But for smaller size input, I mean, again, we only use smaller input for the testing. Anyway, it's a course, and we are not really stressing for the best, most efficient way to do the implementation. But basically, you can actually run the naive recursive version of the not BUC, the optimal binning algorithm, and you can actually get the number, right? So basically, you can actually understand whether your dynamic programming implementation is correct or not. So first, try to get the table correct, and then from the table, it's only it requires you to understand the algorithm a little bit. At least that's the correct way to do that. And you only need to modify the algorithm slightly so that you can also produce the final output. Okay. So we just continue talking about the optimal binning algorithm. So if you recall, the general idea is that we are going to solve the optimal binning algorithm for n input, n values. It's an input array. And we need to put them optimally into B bins. And the optimality is actually characterized by the total square sum errors, SSE, for each bin, and you sum it over all the bins. Okay, so later when we move on to the classification and also in clustering, in many of the machine learning parts, you actually have similar idea. Okay, basically there are many ways to do the same thing. Let's say to classify points, let's say in 3D space, or this carries over to high dimensional space as well. There are actually multiple ways you can draw a line or draw a hyperplane to classify points. But under certain criteria, if you can define a criteria, then you can actually say, okay, this method actually gives you the best way to classify or separate these two sets under that particular notion of optimality. Okay, if you change the notion of optimality, you come up with a different model. Okay, so although the SAC here is actually, I mean, it's just more trying to give you some idea of many things actually are flexible, and maybe in your particular scenario you want to penalize a particular kind of configuration of binnings. Then, if it still satisfies the dynamic programming requirement, you can actually modify the algorithm to do that. Okay, but basically, you actually input n element, and this is actually B bins. The algorithm goes by, again, we talk about the dynamic programming version, is that they try to solve smaller problem first. Okay, the smaller problem is that given one bin, I know how to put any of the suffix. Again, this big S is the suffix of the original input. So I can actually know how to do that, because for one bin, there is only one way to do that. Okay, everybody knows how to do that. And you fill in these numbers. So you fill in these numbers. For example, this one is already filled in. Then, with all these number ready, I can actually work out the second layer. So, for example, if I want to put the suffix 1, which is actually starting from here to here, into two bins, all I need to say is that I need to determine where I should cut. Okay, so basically there is a for loop where you actually cut here, cut here, or cut here. Again, I'm talking about naive solution, right? Actually, if you are careful about the index, you can actually know some of the way to cut is actually invalid. But anyway, I mean, you try all the possible ways to do the cut. And let's say if you decide to cut here, so you actually decide to put them into one bin and put the rest into B-1 bins. Although here it looks like very simple, B-1 is exact 1. But the key idea that B-1 bins has already calculated here. Okay, so you don't need to do the calculation again, even if it's only 1 bin. You just look up the value. Okay, that's the key idea. And you can actually do the calculation. Okay, so at the end of the day, for this kind of table, you are going to only retrieve this one, right? So if you think about, you need to fill in a table. The number of rows is order B. Actually, to be exact, it's B-1 rows plus the final value. But again, when we talk about complexity, it's all in big O. So probably it's easier to, whenever I say B, it's essentially OB, right? And the number of suffix is actually ON, right? Because their input is N element. So the table itself, although the table is actually, not every cell is actually need to be calculated. But roughly speaking, you can do the more careful calculation. But basically, it's going to be NB cells, right? And at the end of the day, when you calculate the 3-star solutions, like all these cells are going to be calculated. Okay, so your running time is at least NB. But also remember that whenever you calculate some solution here, for example here, you need to consider all the possible ways to do the cut. And the number of ways you can actually extract a prefix to put it into one bin is directly proportional to the current problem size. Again, a more detailed evaluation needs some kind of more detailed analysis, but you can convince yourself that in order to calculate each cells, it needs ON calculation. Okay, so that's why the overall complexity of this algorithm is this order. Okay, n squared times b. So this is already much more favorable than the naive recursive solution. In fact, the recursive solution will actually have exponential running time. But in practice, as we said, this algorithm is still very expensive for large N and a large B. As I said, I mean, typically, for example, if you think about stock price or really a large data set with millions of values, this N could be in the order of 10 to the power of 6, right? 1 million is 10 to the power of 6. So N squared is 10 to the power of 12. And the number of bins, if you want to summarize millions of value into bins, you definitely need hundreds of bins, right? So basically, you are looking at some complexity which is 10 to the power of 14. Okay, basically, it does take a very, very long time, even for a powerful computer. And it's, again, even if you can do this, let's say within 2 days, if I increase my N to be 10 times larger, it means you need 100 times, let's say, 2 days. Okay, so it doesn't scale very well with very large data sets. This is mainly because we actually insist on finding the optimal solution. So in fact, I won't mention this, but once you know the dynamic programming algorithm, if you don't insist on finding the best ever quality solution, you can actually do something called approximate dynamic programming, which essentially can say, okay, if the solution quality does not look very good, I don't need to calculate it. But again, that's only going to speed up the complexity by some kind of small factor. It's not going to affect too much. So in practice, if you really have a large data set, we usually comes to this kind of heuristic algorithm called max_diff. And the algorithm is actually very, very simple. Okay, the general idea is that whenever we need to divide, let's say, these 4 items into, let's say, B equal to 3 bins, right? And the input is exactly the same as the optimal binning algorithm. We cannot change the order of the input X elements, okay? And if we want to cut them into 3 bins, all you need to do is to cut twice. Cut b minus 1 times, right? And by cut means, okay, you can determine saying, okay, I place a bin boundary here, or let's say I place a bin boundary here, right? Okay, so if you think about this kind of algorithm is a heuristic algorithm which says, okay, let me enumerate all the places you can place a cut. Okay, so for n element, you actually have n minus 1 locations. These are the candidate positions for a cut, right? So here n equal to 4, so you have 1, 2, 3. You have 3 places you can actually do the cut. So we actually need to, basically the algorithm is almost like a greedy algorithm plus some kind of heuristic ranking functions. So we want to say, okay, which cut is best? And you keep on taking the best option, taking the best candidate cut, and until you actually exhaust all the options, you have already taken b minus 1 cuts. So the quality of a cut is actually trying to say, okay, what's the difference between the value adjacent to the cuts? So for example, for the first cut, it's 7 and 9, okay? So the values are quite similar. So basically this means if we cut here, it's probably not a very good idea. But if you look at the second cut, actually the third one, the value is actually, the left-hand side is 13, this one is 5, okay? If I do the cut here, I can make sure that 13 and 5 never ends up in one bin, okay? And in this small example, you can see that 13 and 5 are the two numbers which are, have the largest difference. And just by the formula of SSE, we know that if 13 and 5 and together with something else ever landed into one bin, okay? The average will most likely be somewhere between 13 and 5, and this will actually incur a large SSE, which means the cost or the error. Okay, so this kind of heuristic essentially say, okay, I want to avoid putting values which are very, very different into the same bin. Okay, use this kind of criteria to rank all the possible positions, and then you keep on selecting the best b minus 1 cut points. Okay, so back to this kind of case, you actually algorithm-wise, you actually calculate gaps between every two consecutive numbers, and you got 2, 4, 8, and then you need to pick up b minus 1, b equal to 3, b minus 1 equal to 2. So you try to pick two largest cuts with respect to the gap value. Again, the gap value should be the absolute value. It doesn't matter whether it's minus 8 or positive 8, right? So in this case, you actually select 8 and 4, and the 8 and 4 actually give you the cuts like these two cuts. Okay, and in this small example, you can actually show that this the solution you got from max diff is exactly the same as the optimal binning method. But this is not generally the case. But even if the max diff doesn't give you the optimal solution, the solution quality is usually pretty good or close to the optimal. So in practice, we use it quite widely. The main reason is because the algorithm only involves one scan of the data set, right? And calculate the n-1 gaps, and then finding the top b-1 values. And this actually can be done in a naive way by sorting, right? If you sort n-1 values, and then you keep, if you sort in decreasing order, then you only need to take the top elements. In fact, if you know some kind of algorithm, you can actually change the so-called quick sorting to quick selection, and you can actually do it even faster. Okay, so, but it's not required, so you can just remember the algorithm is almost like n log n, but although in theory, I mean, you can actually do even better. Okay, so n log n is essentially the sorting cost. Okay, so all the previous methods, also we talk about okay, the equal width and the equal depth binning. They only look at one attribute at a time. So it's easy for you to come up with an example, which this figure gives you some idea that if you only look at one attribute at a time, the binning result you get is not necessarily the best. Okay, so if you look at these, if I have two numerical values, x and y, again, this is artificial example, it's too contrived, right? But again, in reality, as we'll say later, attributes, features or columns or in the dataset could be somehow correlated accidentally or but just by nature. So you will actually see certain kinds of this kind of phenomenon in real data set as well. So if you project the data set into x-axis, you can see that the density is all, let's say if we use equal width or whatever, equal depth binning, you will actually see that almost every x approximately receives similar number of, roughly similar number of points. Okay, so basically there is no way you can cleanly separate them, no matter how you do the binning. So most of the binning method, even for the optimal binning method, will just become something like equal width if the density are approximately the same. You can say the same thing about the y-axis as well. So if you do the binning independently on x-axis and y-axis, basically you will actually almost do equal width binning. Okay. Although if you really can plot the data and look at try to do binning in two-dimensional case, you can actually find ways such that you can clearly separate them, right? So, for example, you can actually have 1 bin, 2 bin, 3 bin, 4 bin, 5 bin, 6 bin. Actually, the solution here actually, so here if you just want 6 bins, you can do something like this. And if you want, I think 9 bins, you can actually do another cut here. Okay. Why don't we try to do this? Okay. This is mainly because of the complexity of the algorithms. So again, if you want to do the optimal binning even two-dimensional space, you can show that this is an NP-hard problem in general, which means there exist instances where if you really want to get the optimal quality binning method, again, optimality can be defined in a similar way as our SSE, right? Whenever you let's say if you put all these points into these 2 bins, essentially you actually, this bin, essentially you actually get the geometric center, and then basically for each point, you can measure the arrow, right? And you sum them together. This is your SSE. So you can show that under this kind of criteria, this is an NP-hard problem. So again, there are heuristic algorithms to do that, but there is little hope that we actually will find a polynomial time algorithm trying to give you the best binning method, even in 2D. Okay, so these options are all related to, so this actually try to generalize, okay, can we do binning in multi-dimensional space? But even with these kind of things, this kind of binning is actually, we call it unsupervised, which means all the data points here, okay, we don't have any knowledge about their class label, okay? You can think about, let's say each point is a person, and you might have person who died because of certain, let's say these are all the patients who actually undergo some kind of operation, right, or taking some medication, and we actually could have some kind of binary outcome, let's say whether the patient survived after, let's say, operation or medication or not, okay? So we have the option of saying, okay, we can do the binning without looking at the class labels if they are really available, because in many cases, actually, they are not available. For example, for supermarket, they actually do this kind of things. It's called custom segmentation. They want to group customers into different kind of bins such that they actually represent the different kind of characteristics. Okay, they actually do not know a priori if they have millions of customers the class label, whether they belong to, let's say, a particular typical kind of customers. So these kind of also method, all the methods we talk about so far actually assume there is no class information. Okay, so the next method we actually talk about quickly is actually what if we do have the class information? Okay, this actually will help us to do binning in a much more sensible way. The detail is actually highly related to a decision tree that we are going to talk about next time. But I'll try to introduce some of the important notion there. So when we come to a decision tree, it will actually become easier as well. Okay, so we actually need to use some kind of information theory, and one important concept is called entropy. Okay, so for those of you, I think you probably heard about this kind of saying that we can use entropy to evaluate the uncertainty of random events. Okay, again, entropy carries over to multiple classes, but to make things simple, we actually focus on binary cases. So let's say we have a class information, whether either positive or negative. Okay. Later I will use example of let's say we have balls, whether this is black or white. Okay. So these are the two classes scenarios. If we know the portion of, you can think about the portion of positive labels, positive instances is denoted as P plus, and the negative ones is P minus. Then the entropy is a function of this distribution. Okay, I'll give you some example later. But if you want to generate to m classes, more than 2, essentially that's the formula. Okay, so the property of the entropy is that if the entropy is high, entropy you should think about something as impure, okay, or chaotic. How chaotic the whole system is. The whole system actually has some kind of randomness inside, and we want to measure how uncertain it is. So if entropy is large, for example, if we think about a set of instances, it only have 2 labels, plus or minus, right? And if I tell you that the entropy is actually 0, or very close to 0, this means there is very little uncertainty in this set of instance S. Okay, so you can almost think about, okay, if I randomly draw one sample from S, so you can think about S as a bunch of balls, okay, in a box. So you randomly draw one from out. Basically, you almost have certainty on what's the label of this ball, whether positive or negative. Okay, so if I give you 100, so if S is 100 balls, right? If entropy is close to 0, it means all of them are black or all of them are white. Or let's say you can think about, if I tell you that 99 of the balls are white, right? One of the balls are black. And then I tell you that if I randomly draw a ball from the box, right, which label you would predict? I think everybody will predict white, right? Because it's, the odds is 99 versus 1. Okay, so this actually, entropy actually gives us a nice way, and there are a lot of mathematic, properties behind it, but I don't think we need that. The main thing you need to remember is that entropy actually measures how chaotic, how random the system is. Okay, so if the 99 versus 1 case, it's almost certain which ball, of the outcome, so the entropy will be very close to 0. And for m classes, the maximum you can get is log m. Okay, log m means, okay, if there are, let's say, 100 balls and there are 4 different colors, each ball have 25 balls. Each color have 25 balls. Okay, and then if you randomly draw one thing, basically the entropy is going to be very large. Okay, because it's very, very uncertain to say which color it is.
So the entropy is maximum when you have a uniform distribution among different classes.
Yeah. That's actually a good question. So if you don't have any constraint on the PI, for example, if you have 4 classes, it's going to be P1, P2, P3, and P4, right? And the only constraint is sigma PI equal to 1, right? And under this constraint, the distribution which achieves the maximum entropy is going to be the uniform, okay? But the interesting thing is that, again, we won't go into that, but later we are going to talk about logistic regression. It's a well-known classifier. You can show that logistic regression is actually trying to maximize the entropy for a bunch of parameters, these are probability values, such that they actually also subject to additional constraints. You can say, let's say, if P1 plus P2 equal to 3 times P3, right? I can add this kind of constraint together with the default constraint. This constraint is essentially means one of the variable is actually, essentially the free variable is only 3 of them, because once you determine P1, P2, P3, P4 is determined, right? So essentially you can think about the freedom of the system is only 3. But if I give you another constraint, P1 plus P2 must be equal to 3 times P3, basically, and you still want to maximize the entropy, maximize the uncertainty, this will actually give you some kind of a model which is exactly the logistic regression. Okay? But anyway, that's we don't require that, but that's actually one of the ways we actually, one of the reasons why, especially for multi-class, we also call it maximum entropy model, because it really maximizes the entropy under some kind of linear constraints. Okay, so if I have a box, okay, and so S is still 100 balls, and this time I say, okay, the black balls are 70 black balls, and the rest are actually white balls, right? Okay, so I can use entropy to characterize how uncertain the whole system is. Essentially, you can think about it. If I randomly draw a ball, I probably will predict it's black, right? Because black is 0.7%. But basically, there are still 30% of chance it's going to be white. So you can actually calculate plug in the number into the formula, you can actually calculate the entropy. Now I'm actually trying to say, okay, if I give you some other information, okay, I might be able to reduce the entropy. So, for example, I tell you that for some reason, I can divide the 100 balls into 2 sets. Okay, you can think about the balls are of different weights. Okay, S1 balls are actually lighter balls, and S2 are heavy balls. It doesn't really matter what does S1 and S2 means. But I tell you further that within S1, it's a set, right? S1 actually have, let's say, I have 72 balls, and just to make, and out of them, the black balls is actually 69. So that the white ball must be 72 minus 69, must be 3, right? And hence, in my S2, the black and white are actually already fixed, right? Black, because I use 69 balls, so it's only 1 balls. And the white is going to be 27, right? Okay, you see the setting. So if I divide it magically, into S1 and S2, and somehow almost all the black balls goes into S1, and which results in the fact that almost all the white balls, not really, but almost all the white balls into S2, then if you think about the uncertainty of the whole system is going to be much less if I tell you which ball, if I randomly draw a ball, not only before I ask you to guess the label of the balls, color of the balls, I also tell you that this ball actually comes from S1 or S2. Right? I give you a piece of more additional information. These information are not given in the ordinary entropy case, right? And then for this kind of information, for this kind of configuration, I think everybody agrees that if I know which set it comes from, let's say if I know it comes from S1, I will definitely predict black, because the order ratio is actually 69/3, right? Almost always win, right? And if it's coming from S2, I will predict white. Okay, although it's not perfect, but it's actually a great improvement over the previous one. And if you think about entropy, it's almost like we are almost certain, if you really give me the information about which subset it comes from, we are almost certain about the label of the balls. Okay, so in this case, the entropy should be close to 0, right? Okay, so you can think about we need a method trying to evaluate how much how much improvements subdividing this big S into two sets gives us. Okay, so you can imagine that if I divide it into another way, for example, also the ball have shapes, but roughly speaking, you can think about if I divide it into S1 prime, S2 prime, right? And S1 prime actually have, let's say, 60 balls, and about 30 of them is actually black, and 30 of them is white, and 40 balls here, and I think you work out. Okay, that's actually pretty good as well. So I need to, let's say, 50 balls. So this is 20, this is 30, and this is 40, and 10. So you get the idea. So if I divide it into different ways, let's say this is an equal split in terms of numbers. The resulting balls, 30 black, actually 20 definitely be white, and the 40 will be black, and the 10 will be white. So intuitively speaking, this kind of partitioning or subdividing of the original set is not as good as the previous one. Okay, you still have certain uncertainties, especially if I tell you the ball comes from S1. Because S1, the black and the white have 3/2, so it's quite uncertain, right? Okay, so we need to measure what's the best way to partition things into two subsets, such that the class information is actually still, the uncertainty about the class information is actually greatly reduced. By reduced, why we are concerned with this one? This is actually related to the binary binning. So if I give you a set of instances, and let's say one-dimensional points, each one actually have a color. Okay, again, you can actually partition them into different ways. Basically, I want to find a way to do the partitioning such that, okay, within one bins, okay, most of the resulting balls or instances are of the same color or of the same class, right? So this can be measured by the entropy after doing the splitting. So how to do that? So what we do is that we can actually use this kind of formula. So if we divide this S into two subsets, S1 and S2, again, there are some kind of plus, there are some kind of minus, right? So I randomly draw some instances. So for the S1, S2, each of them, actually, we can actually get the entropy of S1, and we can get entropy of S2. Now, we want to have a single measure to characterize the whole thing, right? We cannot simply choose entropy of S1, and it's not correct to always choose entropy of S2. This is mainly because, okay, the entropy, to some extent, you can think about measure the whole system. Okay, not every ball are in S1, hence you cannot, entropy of S1 does not represent every ball's, entropy, let's say. So a more scientific way to do that is actually sort of like the weighted average. And the weight is determined by the size. So this is actually the relative size of S1. So there are actually S1 elements. Each of them should be, if you pick S1 elements, each of them will actually say, okay, my entropy is entropy of S1, right? And if you happen to choose someone from S2, they will actually tell you something like this. Okay, and finally, because S definitely equal to S1 plus S2, right? Okay, so if you do the math, if you think about it, it's almost like an average. So if you randomly draw a ball, there are S1 over S probability that it comes from the first set, and hence the entropy you got is entropy of S1, and with 1 minus that probability, it comes from S2, and you will get a value of entropy of S2. So the final average or expected entropy, so that's why this E is almost like expected entropy by this kind of with this kind of T with respect to a particular way to do the partitioning. So this T is a variable just saying, okay, if you cut this operation T, you will end up with a specific S1, S2 subset. You will actually get this kind of formula. And you can show that this value is always no larger than the original value. This actually says, okay, if I give you a bit more information, because this model says, okay, I tell you which subset the ball comes from, it's not going to be, I mean, usually it helps, okay? Although some of the information is much more valuable, the reduced entropy to very low, almost like 0, just like in our previous example. But some of the cuts are not that powerful, but in general, it still reduces some kind of entropy, okay? And in the very worst case, the entropy remains the same. So this actually means that if you refine, give you more information about the whole set, it tends to reduce the uncertainty, okay? And the reduction actually can be characterized by so-called information gain. So far, all this concept will actually reappear in the decision tree next time. Basically, you will see this is a very useful and well-known concept. Okay, so the details about how to use this kind of method to do the binning is actually really out of the scope. But the general idea is that now I can actually try to see, for example, you can imagine that if I have, if you think about a one-dimensional case, right, you have some triangles and some rectangles. They represent a different kind of class, right? Okay. Now I want to do the cut. So the algorithm works by every time they do a binary cut. So cut the values into 2 bins. Okay. So you can actually cut here or you can cut here, right? I mean, and many places in between. So they just want to know which one is better. So with all the previous thing, we know that as long as so this is possible cut T1, this is possible cut T2, we can actually do the T1 given this S. Let's say this is 0.7, and this one will result in T2 of S, let's say 0.3. Which one will we choose? Yeah, T2. Because the entropy is smaller means, okay, basically there are less uncertainty. It's almost like everything in the bin, although this is not necessarily the case here, because I randomly draw a bar. Almost all the points in a bin actually are coming from the same class, no matter from black or white, but majority of them actually come from the same class. Hence, the entropy, expected entropy is going to be smaller. Okay, so that's the general idea. And you keep doing this kind of things. So basically, they require that after doing the cut, after doing the cut, the difference must be at least greater than or equal to some threshold delta. This is because, again, as I said, in general, every time you do the cut, you are going to reduce the entropy to some extent. Okay, but some of the cuts are actually not necessary. In a sense, if you actually after doing the cut, the entropy reduction is very minimal. Okay, so they actually set some threshold so that you can actually guard against almost like useless or trivial cuts. There are actually, I think there are also a formula. Okay, it's not there. So in the textbook, if you're interested, or in the original paper, they actually give you further very complex conditions. They based on, if I remember correctly, the reason they call it MDL is because they use so-called minimum description length principle to really to understand, to characterize when to stop doing the cut. Because otherwise you will keep on doing binary cuts, and you can go to the very finest cut where everybody is in its own bin, right? Okay, so just a quick summarization of what we discussed so far. In practice, it's very, very important to use visualization tools to understand data distribution or some kind of statistics tools. So for those of you who actually already played with pandas, right, if I remember correctly, pandas data frame actually have a method where they give you some important statistics. If it's a numerical value, they actually give you the means and the standard deviation and so on and so forth. And for categorical values, they actually give you a distinct number of values and so on and so forth. So this is almost like it's only one call away from getting the column statistics. In fact, I mean, this is, if you want to know more, and it's highly recommended if you do any kind of machine learning or data science project, you actually want to visualize at least each individual features or dimensions. You can use plotting tools to plot them, and sometimes you can plot the correlation between the two attributes. Again, you can do the plot, or you can actually use some kind of statistical method to summarize the value into some kind of numerical values. But usually, plotting is highly recommended because statistically, for example, if I say, okay, the average salary in Australia is, let's say, 80,000, right? It doesn't really represent a lot of people who actually are below that, or a lot of people, few people who are actually well above the average salary. So although the average do have some kind of statistical meanings, but sometimes, I mean, you might have two columns with the same average values, but their distribution are totally different. So it's better to have a look. And for our binning method, as a general rule, if you do have the class label, using something which makes use of the class label usually works well. Intuitively, it will actually give you a binning method such that if you, again, further apply it to the machine learning, especially classification task, it will, generally speaking, will be beneficial because it preserves the class information within each bins rather than just do some kind of clustering without respect to the class label. Again, we are only able to introduce some kind of basic ideas of the clustering, this kind of binning. There are actually much more sophisticated ways to do that. So I make some kind of comments here because I'm not going to talk about it, but it's highly recommended that after you have learned, especially classification and clustering, you probably want to come back and see a lot of things actually makes more sense now. Okay, and if you have practically runs a few code trying to learn some kind of models, you will actually see that this kind of data type conversion is quite important. Okay, although looks very trivial, but actually we spend quite a lot of time dealing with features, trying to do the type conversion or trying to reduce or engineer new features. That's actually, in many cases, more important than training the model or selecting a particular model. Okay, in the rest of time, I'll quickly talk about this one. Again, these are actually not really required, but I just want to give you a complete picture. Because previously, when we talk about data type conversions, we mainly talk about, you have numerical values, and I want to bin them into several bins, or doing clustering. If we have two-dimensional data, if we don't care about optionality, we can actually use some kind of various kind of clustering algorithm to assign points into clusters. You can think about cluster as two-dimensional bins. It's not necessarily rectangular bins. It could be any shape or demanded by the clustering model. Now we actually talk about the case where actually should be the other way around. Okay, should be the other way around. Okay, should be this way around. So if we do have some kind of discrete values, we want to convert them into some kind of continuous values. Okay, again, this is actually usually, I use some kind of simple example to illustrate, but again, after you learn machine learning, you will see that a well-known thing, actually one of the techniques called KDE, kernel density estimation. And to some extent, many of the machine learning models are doing nothing but trying to recover the density function. So from discrete values, because there are only limited number of training examples. So you can think about these are discrete values, and you want to recover the whole distribution. So that's actually a very essential problem. So let's look at a very simple example. So if imagine that there are some kind of, you were sent by the company to sit at a bank and or whatever. There might be some kind of sensors. They pick up how many customer walks into the branch in a particular time, right? Let's say between 3 and 4 p.m. And you can do the measurement on each day. So if you do the measurement, let's say you get this kind of discrete observations. So this means on the first day of the measurement, there are only 2 customers who actually enter into the branch between 3 and 4. And the next day, 3, 3, 3, 3, 1, and 5, and so on. So let's say that's all the observation you have, right? And we can actually try to answer the question, what's the probability to see x equal to 3 in the new experiment? Let's say you want to predict tomorrow, which haven't happened yet, right? What's the probability that you will see 3 customers walking into the branch between 3 and 4, right? So it almost sounds like a prediction problem, but again, there are more sophisticated models you can use, but let's think about a very simple way. We just use if we don't care about other features, if you like, or the recency and so on and so forth, don't treat it as a time series. I'm just trying to say, okay, this is just a bunch of discrete observations and there is no other information you know about it. What's the best way you do the estimation? So there are actually several ways to do that. Again, I'm not going to go through the mathematics, but the viewpoint is actually more important. Okay, so I think the naive estimation, I think, is actually based on something like this. Okay, so you want to predict x equal to 3. I've already sampled 1, 2, 3, 4, 5, 6, 7 times, and out of the 7 samples, 4 of them actually have x equal to 3, right? So my probability is going to be 4 over 7. Okay. I think everybody should be comfortable with this one, right? It's almost like comes out of, it's almost like, for example, if I say, okay, I'm very good at shooting a target, right? So you said, okay, let's do some experiment. So you give me 10 shots and I try to shoot the target and I landed 8 out of the 10, right? So you will actually give me an estimation that my accuracy is 80%, right? So it's exactly the same thing here. So what is not known is that actually we are doing some kind of so-called maximum likelihood estimation. Okay, so this kind of estimation is, I won't go through the details, but basically this kind of estimation works okay for x equal to 3, but it fails for this estimate. So if I want you to estimate what's the probability that I'm going to see x equal to 4, you look into the samples, and there is no sample out of the 7 that equal to 4, right? So your MLE estimation will be 0 over 7. So if you think about it, this is actually not very reasonable. For any sensible human being, we actually, of course, it can be argued in another way, but we do think if I have seen 2 customers, 3 customers, 5 customers, and 1 customer, although I haven't seen 4 customers exactly, but it's still likely, right? There is no reason to believe that I have seen 3 and I have seen 5, and there is the possibility of seeing 4 is actually 0, or very close to 0. Okay? So this is actually a philosophical view which is actually very important in all the statistical modeling. Okay? Essentially, there are different ways to think about why you actually make such a strong statement about I'm not comfortable with the fact that x equal to 4 should be close to 0. Okay? Even if I give it a very small probability, let's say 0.001, you probably still feel very uncomfortable, right? The general idea that if you really plot the whole thing, if you do the MLE, let's say this is 2, 3, 4, 5, yeah, I think these are and 1. The PDF you will get is something like 1, 1, then jump to 3, and to 0, and kind of, because 0, this 4 is actually very small, right? And the 1, 2 is actually small, and the 3 is high, and the 5 is okay. So if you think about this kind of function, this is the probability density function, or this is for a discrete case, it's a PMF. But basically, the function is actually not smooth here. So because it actually goes down quickly and goes up again, right? And this kind of function, we usually call it not very smooth. So in machine learning or statistical modeling, in many cases, we do assume, there are a lot of reasons. I mean, one of the technical reasons is that if the function is not very smooth, first of all, there are lots of functions which are ill-behaved. I think if you learn calculus, you know that there are functions which are continuous everywhere, but not differentiable everywhere. There are functions differential everywhere, not continuous, and there are very strange kind of functions out there, right? So you are essentially trying to find, deal with functions which could be very, very weird. Okay, you don't really want to do that. You don't want to have a very hard time. Secondly, for smooth functions, we only need very little data to estimate them. Okay, so basically that's the technical reason. So if you think about it, we are not happy with this kind of things. So we are not happy even if we say, okay, this value is we just assign a very small value, let's say 0.1. Okay. By the way, if we do something like this, this is usually called smoothing. And later when we talk about naive-Bayes classifier, and it happens a lot to the probabilist classifiers, you actually apply this kind of smoothing. Okay, and this kind of smoothing in this context, you can think about it's actually quite stupid in the sense that it just avoids the zero estimate. It just tries to give you a small enough value so that it's not zero, but the value could be very, very not smooth locally. Okay, another way is that we actually assume a global model. Okay. This is actually similar to the many of the machine learning things or statistical things that we need to assume data come from some kind of distribution. And for statisticians, that's their favorite approach. So we can actually assume that it comes from a good distribution such that we have a closed formula estimates. It's not technically necessary, but it makes the parameter estimation or called inference much easier. We might have closed form. So again, we won't talk about these kind of models in machine learning, but if you go into Bayesian models, they are actually conjugate prior. And the reason they actually use conjugate prior is exactly because after assuming this kind of conjugate prior, the posterior probability will actually have a closed form rather than numerical forms, so that you can actually have very nice formulas and so on and so forth. Okay, so that's actually a valid way to do that. So one way to estimate the arrival number, a very good model is actually the Poisson model. Okay, so the PDF is written there, but I'm not going to talk too much about it. But essentially, the parameter we need to choose is lambda. Okay, this is almost like average. I forgot whether this is the average. I think this should be the average number of customer arrived during the fixed time interval. So basically, you can imagine that if I give you different lambda, if I give you lambda 1 and the lambda 2, and the different lambda, the probability of seeing x equal to 2 will have different values, right? Because the formula is going to be different, okay? And the probability of giving, seeing x equal to 3 is going to be different values. So which lambda should I choose? Yeah. So this is actually the MLE principle. Again, in logical regression, we are going to see that in more concrete mathematical forms, so I won't expand on the mathematical forms. But the general idea is that everything is possible. But one configuration of the parameter here, the parameter is very simple, only one value, scalar value, lambda, will make the training example or will make the observation most likely. Okay? And if we can solve the equation to find this kind of lambda, that's actually our best estimate under certain sense. The sense is called MLE, maximum likelihood estimation. Okay, but there is another school of view saying that, okay, The other thing I want to consider is actually the prior. Prior means, okay, what's your prior belief? Again, there are actually a lot of things difference between MLE and MAP, but for our purpose, you can think about, okay, you probably have some kind of belief on what's the most likely lambda. For example, if I just ask you how many people come into a branch between 3 and 4, you might say, okay, by my experience, right, I believe it should be around 3, okay? Or your view could be 10, okay? It doesn't matter. So then you try to sort of like maximize the likelihood combined by the prior and also the likelihood of the data, okay? And this will actually give you some new estimate called MAP estimation. Again, all these kind of things will happen again in the naive Bayes classifier. So you can see that although we are discussing type conversions, but the idea actually carries over easily to many other statistical models. Okay, so even if we do something like this, no matter which one we use, the drawback is that we are assuming a global model. Okay, so if you ever know that, one of the problems with the statistic is that in reality, okay, the data does not always conform to a well-known, model. Of course, you can say, okay, the data come from mixture models and so on and so forth. But in practice, I mean, if we can really model it very accurately with a few well-known or close formula distributions, things will become much more easier. Okay. In reality, I mean, things are actually not that good. So simple. So trying to assume a global model is very, very hard. Okay. But much simpler thing can be, we can actually assume a little bit less. We can actually assume that we cannot say much about the global distribution, right? All I know is my local distribution. Okay, so again, I won't go into detail, but this gives us to a well-known technique called the KDE. It's called kernel density estimation. The general idea is that once you saw, let's say if I saw x equal to 3, right? You can imagine that if I know my number is between 0 and 10, let's say 10, let's say I have the knowledge that the number is definitely going to be between 0 and 10. So if I see 3, the MLE estimate will say, okay, if I only have this example, the best thing I know is that the probability of x equal to 3 is actually almost like 1, and everything else is 0, right? But we can actually have a local smoothness or local whatever model trying to say that if I ever see a sample, because I know the distribution is going to be continuous. Again, so here continuous is continuous with respect to 0, 1, 2, 3, 4. Because I want to use a discrete distribution, it's easier. But anyway, you get the idea. So if I saw x equal to 3 ever, there is a high chance that I'm going to see x equal to 4 and x equal to 2, right? Okay, I think that's the general intuition. If you believe in this kind of things, essentially it means, okay, just putting all the probability mass on the point you have observed is not a good idea. A better way is to distribute it over the entire domain. So if you are more conservative, you can say, my distribution is something like this. Right? The general idea that if you sum up all the probability mass under the curve, it should be 1.0. Okay, so the only difference that previously you put 1.0, it's like you bet everything on one single point. Now you actually have a smooth distribution. Whenever you see 3, you actually place some kind of probability mass around 3. Okay, the shape of this distribution is actually your kernel, specified by the kernel function. So typically, one of the widely used kernel function is Gaussian kernel. Of course, there are other kind of kernels, and some kernel have actually better properties and so on and so forth. Okay, but that's not the most important thing. The important thing is that you actually try to distribute so even if you observe one point, you actually assume that the value in the surrounding point are equally likely. Not equally likely, but still likely. And usually the kernel function have the property that if the value difference, let's say if this is your sampled point, xi is your observed point, x is a new point, and if x and xi, one of the i's are very close to each other, the property is going to be higher. Okay, so you just want to say, okay, if I observe x equal to, let's say 3, any value close to 3 is likely, but let's say 10 is, I cannot say much about it. So you only assume a local model. Okay, so if you do something like this, you can actually, by using this kind of formula, you can actually have a whole distribution of all the, what's the property of seeing x for any of the x in the domain. Okay. And you can see, okay, so basically there are some kind of parameter h, but basically, you will see that if I'm a very conservative, I will actually put h to be a smaller value. So basically, if you observe some kind of discrete points, the final distribution will actually become something like this. So you see, it's not very smooth. You have spikes and a huge change. But if you have a wide h, the final distribution will actually have something like this. Okay? Again, h is a parameter you need to choose in most of the cases. Okay, so let's have 10 minutes break, then we continue. No, Gini next.
Because, yes,
The physical meaning is actually something like the average error. But anyway, I mean, you can think about it as some kind of statistical measure.
Yeah, what have you done?
I've done it's like the second
It's
version.
almost like
But then
the functionality is almost the same as entropy, but it's coming from another angle. So entropy is purely coming from information. It's actually from the average expected classification.
What other subjects do you do?
Accuracy or something like that.
I have project.
Yeah.
If I have a bunch of data,
Yeah.
is there any way to see which model does
So you want to do something
better?
Yeah, maybe. I thought
I see.
maybe
That's actually for the model selection. From statistical point of view, actually there are actually goodness of it. There are actually
That
both
was some part of data
parameterized version and non-parameterized version. But I think if we look at it more like a realistic scenario,
I do have
we
work
usually use
permit.
something called cross-validation, trying to see
You
which
applied
model
for
fits.
Google internship.
Okay.
The general idea that
Yeah, I've done Google
actually next
summer,
slide
but
we'll be talking
if you
about
want to do
translation.
something geographical, Google Maps seems like a good thing
I
to
can
do,
do
so you should definitely go and apply.
And use the rest of data to build a model.
Yeah.
And look at how the reserved data fits into the model. And do this over again, and you get some kind of average performance of whether the data is really.
Yeah, you need to
So I should do that with,
but to like definitely go and apply. Google is really good at like trying to develop.
even with kernel. If I can, if I want.
Yeah, in theory you can do that. But again, from a statistical point of view,
yeah. So
cannot do too much of such tests.
Yeah, so I
Because
work
you run the risk of so-called multiple tests.
called the rock. They're in this
No, just to decide
So basically, they use machine learning on big data to find the perfect
I have
match
the
for
data
customer who just bought something. What else might be interesting? So
Ah,
yeah, they're really cool. They're quite small yet, but they're all in
I mean,
CC.
it's a very large field. But the general idea is that if you have a lot of hypotheses, you say, okay, the data should come from Gaussian or
So you there as
whatever.
well. Yeah,
And then
seriously.
develop a very powerful, very
Definitely need more girls.
solid
They're like
test condition.
40 engineers and only 2 girls.
If you compare too many of them, which fits the best, there are high chance that the model you finally selected is not the this is for the multiple test.
We have like
To give you a very simple example,
commerce type, like full stack development.
okay, let me tell you, okay, there are
People who are using
it's a real
distributed
story.
technologies to like
There are scams that's really can use an email saying that I can predict the next let's say NRI or match results, which team will
But
win.
first try to apply to
Okay, this
Google.
is a scam.
If it doesn't
When you look at the result, and this week the outcome is correct. So every week you actually
I know it's quite hard to
match.
find job afterwards.
Every week you actually
Because there are not that many software companies.
So basically it's a perfect fit of the model.
Yeah, yeah.
Then
Yeah,
then they send another email saying, do you want to bet on the 11th match? You need to pay, let's say, $50 or $5. You probably will think, okay,
Google
since they performed so well in the past 10 years, okay, they must know something.
Yeah, yeah.
But do you know how they operate?
What did
They
you
operate the master match. They actually send for every match, they randomly select actually 1 million victim, right? They send randomly half of them say, like
distribution.
is free.
like, sure.
Approximately 50%.
Like we write the formula, exponent.
But after 10 rounds, you still got
I understand.
if you start with
I
1 million, you
did
still got 1,000.
actually do two separate degrees. I have a bachelor in bachelor in applied mathematics. So, yeah.
So you
Yes, so I also done some mathematics.
Just by chance.
But you can definitely differentiate between people who've done some math and people who haven't. It's like different worlds.
Full test.
It's called a multiple test. Yeah. It's hard to get your test around, but in practice it actually causes a lot of problems. Because for example, another thing is that whenever you have a DNA or blood on a crime scene, okay, you should see, okay, we just compare with the database of all the suspects. This is actually one instance of multiple tests.
Yeah.
So you should discount the importance of match. You cannot say, okay, DNA,
Quite
I think all this DNA or
I barely managed
whatever
like
sperm, whatever, actually
that's
is
high.
very, very high. Anti-power, whatever. The things you are doing with the test, the power,
yeah, we'll see how it goes. The previous
Yeah, because
semester
it's going to be much longer, right?
no, it's mainly, again, there are, on Wikipedia, I think there are lots of outside in whatever, there might be more accessible things. But,
Because I didn't understand everything, what is the plan? Okay, if I work and I get a bunch of data, right?
the lesson is that, okay, the theory just tells you that you cannot prove any hypothesis. In practice, you usually, based on whatever thing, especially if you have some kind of prior experience, you usually try to use the simplest model, which fits reasonably well with the given data, and you think, okay, that's the model, that's the practical.
Okay. All right.
Okay, we go next.
Thanks.
Hi.
What is this K here? Is it the weight there or something?
So you know, like how we say X normal. That's what you say here. That's
It's 3 out of 5.
You can see what the whole purpose of that at least for our type of eliminate the proteins in carbon. before I do this one, this is before I do this one, I need this one. So if I can get these two guys ready, this one is simple for me. So this is the same thing. As I already mentioned, if I get this part ready, anything with any data which is such as surface of the original set, unit tunings actually can be really effective. So you write the previous finally the value you are after is this one. Recursion works the other way around. You ask this one, what should be the value of this one? And then they actually say, okay, you might be doing this, you might be doing this one. And this one will actually recursive other things. And there are a lot of redundancies. If you ask this one, people actually will ask this one. Will ask this one. Oh, 10 years is a function. Right.
Like a multi-density type of function, right?
Okay, it's fairly hard to give you a very good characterization. You don't really have some meaning. But roughly speaking, I think you can think about so again, the way I wrote it, because I just copied from Wikipedia, so it's not a bad way. It actually is x minus x. But you can actually write it as x over h. Because the standard form of the SVM is like it takes two values and it gives you something how similar. So that's why, yeah, you can interpret correlation of similarity. It's a general notion of similarity. It does in mathematics. It only needs to satisfy a few properties. It doesn't care about semantics. So you can interpret this as a general correlation
And this parameter h, can we learn this h while we are learning the data? So like,
I think there are actually lots of advanced mathematics. All the things we can introduce is just very basic idea. So in theory, you can actually at a different point you can use different actions and so on and so forth. I'm not really doing research in this area, but I'm pretty sure I can come up with a few modules that you can change edge or trying to learn the best action. But if you just want to do it, the most standard way is that you try to use some kind of default edge or you use cross validation to select some action. That's usually the first thing you want to try.
okay.
Because apart from edge, you also can select different kind of kernels. Although Gaussian is the most likely kernel, but there are other kind of kernels you would like to choose.
Okay.
For example, I don't think that, later I'll talk about the visualization. There is one famous method test by Hinder, the guy who is the father of the deep learning. So basically, they actually use a similar kernel function as well. And in practice, what you do, I mean, if you look at secular implement that one, usually you only need to tune, if you decide on the Gaussian kernel, you only need to tune the edge. But in theory, you can actually supply a custom kernel function. So, yeah. So in SVM, it's the same thing. Lots of problem library allow you to have a custom kernel function and it still works. Because from a mathematical point of view, they just try to solve some kind of function minimization problem as long as the kernel function respect a few properties, which are very naive, I mean, very innocent properties. Yeah, exactly. Yeah, if you search for KDE on Wikipedia, you will see different kind of functions. Some of the functions actually have some kind of functionality under a certain function. Again, in practice, they're always theory part tells you that there are 6 functions. But in practice, usually I think the general rule that the kernel shape of the kernel does not matter too much, but the bandwidth of the kernel. Many of the kernel do have some certain very similar properties to bandwidth. Bandwidth is much more important. Bandwidth essentially is give you, it's like determine whether you are more conservative, saying that if I only see this value, I don't want to say anything very far from, immediately far from this value. If you have a larger bandwidth, I'm pretty confident to say anything is possible.
One more concern is like sometimes I have other like subject like exams, so I'm actually not in lecture.
Yeah.
When I watch lecture recording again,
If you
it's
log
cut
into the
off.
Moodle,
Yeah, it's cut off. Like it's cut up around
I think-
2 hours, 50 minutes.
oh, really?
Cut off like 10 minutes.
Okay.
Or 50 minutes.
In theory, they told me that should be 5 minutes before ends.
Yeah, so it's cut off like 2 hours.
Okay, yeah, but there is nothing I can do. I think now, I mean, you can complain to them, but
Right.
I think.
I mean, you can rush it, right? You can like, people
okay.
at home.
Try to make sure I don't use the last 10 minutes.
Yeah. Like you can like just before it's finished, before it's actually over, you can like people at home hear important point that I don't say next. So,
Okay, I see. That's a good suggestion.
Yeah. You rush it. You stop about all the important point. You don't really give more example.
Okay.
So,
Yeah, no problem.
all good.
Okay, yeah.
Thank you.
Okay, no problem. Okay, let's resume the lecture. There's one last part that I probably will quickly go through. It's called data reduction. It actually is a quite important method, and there are different kind of strategies. Well, I cannot write. Here, actually, dimensionality reduction is a very important topic. And some of the methods, let's say PCA, is actually almost, if you really have a large number of columns or features, later you will see, and you have limited training data, or for a lot of reasons, you probably want to do PCA first and train a simpler model and see how it works. And in many cases, even it looks like it reduces the data, but in fact, in many cases, it actually improves or does not hurt the performance of the model too much. So there are good reasons for that, but we probably won't have time to talk about that. There are also, again, PCA or SVD, they can be thought of as a way to do the data compression. Of course, I mean, that's probably not giving you the best compression rate, but you can think about this as from a data compression point of view. There are actually quite a lot of machine learning theory kind of things based on these kind of things. For example, one of the theories is called the information bottleneck. They try to say many of the models are trying to compress the data, but still achieve good predictability for the future data. So many of the, under that particular view, I mean, many models just trying to achieve a balance between the two. Anyway, I mean, that's one of the theory. I think what I probably will spend some time is that in practice, it's very common to have high dimensional features. Basically, you have a data set where you have a lot of columns, okay? And there are very good reasons. For example, in machine learning, when we talk about later, we are going to extract a lot of features. For each of the data sample, we are going to look at the features. And for example, one of the example I gave is there are about 500 features. So 500 is already a high dimensional data set. Typically, I think anything more than 20 dimension, or even, really depends on, it's not a fixed number, but if it's more than 20 or more than 50, it's definitely high dimension data. Although some people are talking about high dimension as for text classification or for some kind of, let's say, collaborative filtering, you have millions of dimensions. These are really, really high dimension as well. But in practice, I mean, anything more than 20 or 50 is already giving us a lot of problems. So there is a very famous phenomenon called curse of dimensionality. So that it actually manifests itself in a large number of ways. Okay, I'm not going to talk about all of them, but the important thing is that a high dimension data is extremely sparse. Okay, the reason is that, relatively speaking, you can think about high dimension space as a space which is very, very huge. It's gigantically enormously or colossally huge. So if you throw in 1 million points, because the space is so huge, it's almost like a universe. So they won't be close to each other. So that's the general idea. Okay. So I just try to give you some kind of idea. I think I have some slides. Okay. Yeah. For example, I just pick up this fact. So basically, high dimensional space is actually very different from low dimensional space. So if you think about in 2 dimension, right? If I have a unit cube, the length of the size is 1, right? Basically, the area is actually 1, right? And if you have something like a smaller cube, which is 0.9 on the sides, a smaller square, the area is 0.81. So 81% of the area is within the smaller square, right? So you can generalize this to 3 dimension, to 4 dimension, up to D dimension, right? So in D dimension, again, I cannot draw it, but just imagine this is D dimension. Each side is just 1. So the outer cube, the volume is still 1 to the power of D, right? Still equal to 1. So if you have inside the cube, each size is actually 0.9. The volume will be something like 0.9 to the power of D, right? So anybody know 0.9 to the power of D? Is it going to be a large or small value? Very small value. If you are looking at D equal to 100, you can do the calculation, but it's going to be close to 0, okay? What does it mean? It means a smaller cube, on each side, it's already expanding 90% or 99% of the size, but it only encloses a tiny area of the volume, whole volume of the outer space. And hence, if you randomly put many points into the unit hypercube, you would expect, because the inside, if you think about this is the kernel, the core, only takes, let's say, 1 millionth space. So most of the points are actually on a very thin, on the surface of the hypercube, if you like. Right? That's the only logical explanation. Okay? So if you think about, this is actually very different from low dimensional space. In fact, again, there are actually some very good blog or whatever discussion. I'll give the URL below. This is the picture coming from them. So in high dimensional space, look at this picture. Again, that's almost the best thing we can draw, because there is no way you can draw a D-dimensional cube, hypercube on 2-dimensional space. Okay, but you need to imagine that the space really does not look like an ordinary cube. It looks like a very tiny core with a lot of spikes. In fact, each spike is almost like a corner. So because if you think about in 2-dimensional space, you have 2 to the power of 2 corner, like vertices, right? In 3D, you have 3. If it's 100 dimension, you have so many vertices or corners. So if you just randomly put 1 million or even 1 billion points, and by this fact and by the number of by the fact that there are 2 to the power of 100 is much larger than 1 billion or even 1 trillion or whatever, right? You can do the math. I believe the number of atoms in the universe is 2 to the power of 80 something. So it's a gigantic number. So most of the examples, you can see dog and the cats are actually on some corner somewhere in the universe, okay? But we just don't know where it is, and they do not communicate with each other. Just like when we study stars, right? I mean, if the star is too many light years away from us, I mean, even if it died, we haven't received a message yet, right? So it's almost like something like this. So there are some kind of interesting things. If you are interested, I mean, when we go into classification or machine learning kind of models, high-dimensional thing actually comes a lot. So I just want to show you that dimensionality reduction, for example, we just mentioned, is not necessarily a bad thing because if you really work with high dimensional data, this kind of curse of dimensionality causes a lot of problem to your learning or the model. So sometimes if you do the reduction, it looks like you lost some kind of information, but essentially you make the model much easier to learn and learn more robustly. So probably that's the main message I want to talk about. So there are a few dimensionality reduction methods. That's actually very, very practical stuff. They can be mentioned as a feature selection or feature extraction. So selection is that if I have 10 features, or yeah.
Can we improve the accuracy of the model by applying reduction?
Yeah, that's exactly my point. In many cases, I mean, instead of working directly on the high dimensional data, you actually do some kind of dimensionality reduction. It actually improves your model. Because in the original space, it's too hard to learn anything, essentially. Okay, so feature selection means if you have 10 features, 10 columns, I can select some of them. Okay, and the feature extraction means, okay, I can re-engineer. So a popular way to do that is actually linear combination of the columns. So that's why it's related to linear algebra again, because there we actually look at, fundamental preliminary operation that we can actually, for each of the column, if you think about them as vectors, I can have a linear combination of them and produce a new column. So that new column could be a very good feature, engineered or extracted from the original features. So the feature selection, again, when we basically in the standard library or in many cases, essentially we can actually do some kind of greedy search, or there are actually more intelligent algorithms. But basically, we can actually say, okay, I only select, there are certain criteria, we can actually rank all the features, and we can start with all the features and remove the least important one, or we can start with the most important one and gradually add more features. That's called stepwise forward or backwards. That's the most widely used. There are other more intelligent methods to do this as well. For the feature extraction, arguably the most important one is actually called PCA. So I won't talk too much about this one, but if you want to use it, I mean, almost all the libraries have it. And in fact, I think there are libraries where they actually look at how to do PCA for a very large amount of data and more quickly and try to do it in a more robust fashion as well. Okay, so I won't talk too much about it, but basically the PCA actually do something like this. So this is a good visualization coming from that GitHub page. So you can see that if you look at the blue points, these are the original points. They live in two-dimensional space. Again, we can only do visualization from 2D to 1D. 3D probably is doable, but it's probably very, very hard to see. Okay, so you can see that if the two red lines, actually the main red line is that we try to reduce it to one-dimensional space, but we use linear projection. So we use the linear method to do the transformation. Okay, so if you recall our linear algebra, each point here is just like UV, two-dimensional vectors, right? And if you want to reduce to something called Z, basically, there's a matrix operation to do that, because essentially you map a two-dimensional vector into one-dimensional vector. And this kind of matrix is essentially a projection matrix. And again, it's still keep rotating. So you can see that each one, for example, this one actually project to here. Anyway, cannot trace it. But you can see the points they projected. So the PCA will actually give you the best projection direction. I think probably this one, such that the two conditions are satisfied simultaneously. So these two conditions actually get at the same time. Okay, one is that basically some kind of information or distinguish, or basically some kind of variations of the data set after projection is maximally preserved. And also you can think about if I use the projection to approximate each data points, the residue is actually the line, for example, the line to the projection. The total distance to some extent, is actually minimized, which means if I use my one-dimensional points to represent my two-dimensional points, it's actually almost, in some sense, the best approximation I can have. Okay, so PCA actually will give you this kind of guarantees, and it's a standard method to analyze a very large amount of data. And if you ever heard about something called eigenphase, whatever, it's a canonical example where even for image, okay, if you want to, again, this is a very old method, but if you just grab every people's facial image and put them into a vector and run this kind of basic PCA or SVD algorithm, because PCA and SVD are very similar, kind of highly correlated to each other. Basically, you can actually do some kind of face recognition as well, and it's you don't need any more complex models, just like PCA. Yeah.
Question: do I understand correctly that we choose this projection that keeps the most variance?
Yeah, exactly. And at the same time, the distance distortion is, the distance lost is actually minimized as well, because they add up to the original distance. So that's why you can get it simultaneously. So when we talk about linear projections, so PCA is actually the optimal under certain criteria, especially if our criteria is to maximize the variance preserved or minimize the distance distortion lost. It turns out that if we are really dealing with very high dimensional space, a seemingly very simple way is actually to use some kind of randomized projection. So I won't go into the details, but essentially it means I probably will just, probably we just explain what this formula means. This means if you have a data set X in a high dimensional space, this is D-dimensional space, I can always reduce it into a smaller K-dimensional space where K is actually in the order of log n, and this epsilon is the quality. So how close, how much error you allow, okay? But roughly it's big O of log n. Okay, so if you have 1 million points, log n is about 20. So you can actually reduce a high dimensional data into a low dimensional space such that any pair's distance in the original space is approximately well preserved in the projected space. Okay, you can think about this is, let's say, 1 million dimension space. You have any 2 points, xi, xj, and they actually have certain kind of distance. So that's the distance. This is the, if I didn't say this, usually it's the 2 norm, so it's just the Euclidean distance. So there exists a linear mapping into a smaller dimension space. This is xi, this apply this f, this is apply this f on xj. So the distance here and the distance here only differ by 1 plus or minus epsilon. Okay, so this means, okay, you don't need to use so many dimensions to if all you care is pairwise distance, or in many cases, angles or whatever, it's all, many of the measures in high dimensional space are actually approximately preserved in a low dimensional space if you can find this kind of mapping. And you don't need to know the theorem, but probably the understanding is important. And in fact, this kind of mapping is very simple to construct. Essentially, it suggests a random mapping. Again, the random is not uniform random between -1 or 1 or something. It's actually a Gaussian. So if you construct a mapping, linear mapping, which every component of the projection vector takes from standard Gaussian. So this is a normal distribution with mean 0 and standard deviation of 1. Then with high probability, this kind of projection actually preserve a lot of important characteristics in the original space. But what you gain is that you actually have a much smaller, much more compact space to work with. Okay, so that's probably the most interesting things about this kind of linear projections. Okay, so that's basically we have 2 kinds of linear projections: PCA and this kind of random projections. So random projections actually have non-theoretical properties. PCA do not have that, but in practice it actually works pretty well as well. Okay, I would say that in practice, you probably want to use PCA first rather than using random projection. But this is actually some of the experiments showing that, okay, if you build some kind of model using random projection versus PCA, random projection, every area using random projection and SVD. SVD is close to PCA. You can see that the error is actually very minimal. Okay, you cannot see because there are dots there, but roughly speaking, they are actually around just around the zero. So it only introduces very smaller number of errors. Okay, so all the methods we talk about so far is actually linear transformation. Okay, so when we go to nonlinear transformation, things actually can be done much better. So again, these are just to give you some idea of what you can do. We won't talk about the details, but basically there are actually methods where they apply some kind of nonlinear transformation so that a high dimension data, actually the local structure can be better preserved in the low dimensional space. So you can see different kind of color. So these kind of red points, after doing the linear projection, should be close to the red points. They should not go to the other, because if you look at the three-dimensional space, these kind of red points are going to be close to the blue ones. But in the projection, red and blues are actually well apart. Okay, this actually requires us to do nonlinear projections. So again, this is actually one of the handwritten digits dataset, MNIST. So basically, after doing the PCA, you can see that it's very fast, but I think this is 1, this is 3, this is 5. So roughly speaking, 0 is still here, 1 is somewhere here. So they are kind of separated, but again, it's not very clear. But the good thing that it's very fast, okay, and it's linear projection. So at least a lot of properties we have good understanding. So there is actually a nonlinear. One of the state of art nonlinear projection from high dimensional space to low dimensional space. Here, two-dimensional space is called Tisney. So I want to actually use some kind of kernel function we just talked about in KDE. Okay, but essentially it will give you much better cluster qualities. But of course, I think I get picture from scikit-learn, whatever. So all of them are actually available in scikit-learn. So you can see that first of all, the running time is actually much higher, right? And the MNIST is not a big dataset. Okay, so you can see the difference. Whenever you go to the nonlinear part, it's going to be more powerful potentially, but trying to find a good solution actually takes a long time. And also in practice, I think there are at least some people argue that the result is actually kind of random. So sometimes you get good, because the whole algorithm is kind of have some kind of randomness. So sometimes you get good results, sometimes you don't. Okay, so if you really want to use this one, you probably need to try a few times to see if you can end up with a good visualization. So again, I won't talk about this one. So this is actually adversarial autoencoder. So this is like a deep learning kind of things. Basically, it actually can do better clustering about different kind of. Although it's called unsupervised clustering, but basically it's trying to find clusters as well. So each row. So you can see each row is actually a cluster. So there are some kind of arrows. For example, this 3 looks like very similar to 5. But you can see that there are great variance in terms of the width, in terms of shape, and so on and so forth. And this method can still find it reasonably well. Okay, so that's all I want to talk about the data reduction part. Okay, let's quickly talk about the classification, introduction to the classification part. Then let's see if we can finish the logistic regression part. So we move on to the next part, which is more related to statistics and machine learning. So we are going to talk about arguably the easier task. It's called classification or regression. So we talk about the some kind of definitions. So classification task essentially assume that each of the data points or each of the case objects that we are going to deal with have some kind of class labels. Okay, and usually class label is depending on whether the class label is a discrete set of values, where we usually call it classification. If the class label is some kind of continuous value, it's usually called a regression. So two examples. One example for classification is that you want to determine an email is spam or not spam, right? So the outcome is only two, spam or not spam. Regression problem could be that you want to predict the property price or predict the stock price, predict the sales volume of a particular product. So the value you want to predict is a numerical number, and you can compare with the ground truth, right? So again, I think everybody knows that nowadays there are this kind of task is very important. I mean, you can do a lot of things. For example, you go through the border. Nowadays, I mean, if the machine can recognize your face and verify against the database, I mean, things can speed up quite a lot and also can serve a lot of good purposes, right? So just a few mathematical definitions about and the symbols that we are going to talk about. So the key things I want to emphasize that for classification and regression, we are looking at trying to learn a function. And the function will essentially classify an object. It will classify some kind of object into a predetermined set of class labels, no matter whether regression or classification. But before we can deal with any object O, so you can, I tend to call this object because it could be a document, it could be an image, it could be a video, it could be whatever things. So some of the things actually have, you can easily think, okay, you can represent it numerically, but in many real cases, or for complex things, basically the object actually is an object, okay? And the first job you need to do is to do the feature extraction. So what we do is that we need to map this O to a particular vector. We actually call it a feature vector, okay? So assume that we extract D different features, okay? Then we can forget about O, okay? We only get the, if O, we have example in the next slide, but basically if we got a corresponding vector, D-dimensional vector about O, later throughout all the learning, I just view this as a point in a D-dimensional space, okay? So what I want to mention is that this kind of feature extraction or mapping is not going to be one-to-one, okay? It's entirely possible that you have two different objects. Under your particular feature extraction method, they mapped into the same feature vector, okay? So that's one thing you need to keep in mind. But in the rest of the task, we only need to deal with good mathematical objects, which are vectors or matrices in most of the cases. So we only need to deal with them. So all we need to do is that we need to generate a predicted output. So we actually call it small y for this x. And for classification, we actually just assume that they are actually discrete sets. And as a convention for binary classification, we usually use -1 + 1 as the label. So sometimes we call them positive and negative class as well. But sometimes we actually can use 0 and 1. So they don't really matter, but this might give you some kind of confusion if you just remember the formula without really go through the process. Because, for example, in some of the textbook or notes, they actually assume that y is 0 or 1, so they can derive some kind of formula. And in some other textbooks, they actually use -1 and +1 for the same model. For example, logistic regression we are going to talk about. Then the formula looks very different. Okay, so both of them are correct. The only difference is that they actually assume y is -1 or, one of the classes is -1 or 0. They use different kind of things. For example, in SVM, we actually use -1 and +1. I think in our derivation of logistic regression, and the same is used in deep learning, they actually use 0 and 1 because then a certain formula becomes much simpler, okay, to deal with. And also it's corresponding to the probabilistic model much cleanly. So we won't talk too much about the multi-class classification, but one of the trivial way to do that is to encode it into a sequence of numbers. Although I just want to say that there are recently people are talking about something called extreme classification, where the output class is actually in the order of millions or even more. Okay, in that case, a naive, a straightforward classification probably is not the best way. At least usually it doesn't work very well. So just pay attention that if you do have lots of classes, extreme, let's say, typically thousands is already giving you some kind of problems. You probably want to model the problem slightly differently. Okay, and whenever we talk about machine learning or this kind of learning models, what we really do is that we try to learn some kind of function. Okay, the function maps a vector in t-dimensional space into the domain of y. Okay, so if we are doing regression, the domain of y is going to be a scalar value, so typically a real value. Okay, so that's the general idea. And although we focus on classification, later when we do the derivation, we'll see that we usually, in many of the classification methods, essentially they are trying to solve a regression problem. Okay, so although we don't talk too much about regression, but basically under the hood, regression is actually widely used. Okay, for a lot of good reasons we'll mention later. So just to give you some examples, so think about this example where we want to classify a news into predefined categories of politics or sports. Okay, we only care these two. So basically the document here, I just show the header of the document. So you can see that it's an object. Okay, our first job is to convert this particular object into a vector in d-dimensional space. Okay, so there are a bunch of ways to do that, but one of the simple way is to say I actually generate an input feature. I think there are some kind of misalignment of the symbols. Yeah, I think some of the formula is not there. But basically, we actually can say that I can create a function where the input is actually all the words in a dictionary. Okay? Although you can actually limit your words into the possible words which occurs in the data. And I just count what's the frequency of this word within this document. So this function will reduce, you can think about this is almost like a nonlinear kind of, because originally the object is not in a vector space anymore anyway. So yeah, it's not the best terminology, but you can think about this function just map an object into a scalar value. So for this function, it will actually map this document into the value of 2. But you can actually change the parameter. So I can say, okay, what's the frequency for basketball? So it doesn't appear in the document, so it's 0. So if you go through all of the vocabularies, okay, this document is successfully converted into a potentially very high dimensional vector. The dimensionality will actually equal to the number of words in the vocabulary. Okay, and each number is how many times it occurs. Okay, but later when we talk about text classification, we can see that it's possible that instead of using frequency, you just say appear or not. You can actually say, okay, I don't care about the frequency. I only care about whether this word appears in the document or not. So each of the feature will actually become a Boolean value, will be 0 or 1. Okay, so it's really up to you. Okay, to convert this document into a feature vector. So this is usually called the feature vector for this corresponding object. Then we need to learn a function where a function applied on this x will give us either +1 or -1. Okay? And the function is usually parameterized by some theta. So sometimes we write f theta here, or sometimes we actually write in this way. So if we use we actually write the theta here, it means actually, again, both x and theta could be vectors. Okay? If you're, in many cases, I mean, there are more than one parameter that you need to learn in your model. So theta typically is a vector, and the input feature vector is definitely a vector. So basically, you can imagine that if I use different theta, if I use theta 1, I might be doing, for this document 1, my prediction might be correct. Okay? But for document 2, my prediction is incorrect. Right? But if I use theta 2, this could be both correct. Okay? So intuitively speaking, we probably want to prefer theta 2, right? But later you will see that we need to do it in a more scientific way, and we need to define some kind of objective functions that we want to optimize. Okay, so I was quick. I won't talk too much about the images, but it's exactly the same thing. You can actually go through the example by yourself. Basically, it's another, for each of the image, we need to extract some kind of numerical features out of it, and so that we can convert it into some kind of feature vectors. So here we just use something called a color histogram. Basically, it says, okay, what's the number of pixels? Again, before doing that, you need to pre-process your data such that each picture is of the same. Typically, I mean, you can do this, or otherwise, the pixel count should be relative, should be a percentage. Okay, so it's up to you. But if you can, for example, for MMIST or for many of the facial recognition data, they already pre-process the data so that each face is the same size. Let's say 100 by 100. So then all you need to do is to just do the count. Okay, if the picture of different size, you really need to do the pre-processing, which we just covered, before you can actually do this kind of feature extraction. Otherwise, I mean, the number itself, the absolute value the later machine learning module sees is not really corresponding to anything meaningful, right? Then in this case, you don't really expect that your model can predict things very well. Okay, so so this is for the image. So how to find this f? As we said before, if we can, usually different f, so whenever we say this kind of function f, we are really either explicitly or implicitly restricting ourselves to a class of good behaving functions. Okay, as I said before, there are actually functions which are very, very weird. Okay, one of the things is sine x 1 over x, right? When x close to 0, it actually fluctuates so quickly that basically it's really hard to do anything about it. So we usually restrict f belong to a large class of f. Okay, sometimes we say it explicitly, sometimes we don't do that. For example, for most of the models we are going to talk about, it actually belong to the class of linear functions. So we only consider linear functions because a linear function is already, I mean, it's arguably one of the simplest functions we can study. And even for linear functions, if we define different kind of criteria, they are going to give us different kind of models. Okay, so basically we need some kind of additional input to say which function, even within the linear functions, are good. So we need a set of training examples. So these are the examples where we do have the input x, which is already object converted to the corresponding feature vectors and their corresponding label yi. Okay, and we usually make the simplifying assumption called IID assumption, and we are saying that okay, both the training example, I mean, first of all, each and every training example pairs xi and yi are identically and independently chosen from some hidden unknown distribution. And also the testing data, when we talk about, when we try to evaluate which model is better, which classification method is better, we also need to use the same distribution to generate some kind of test data and then see the performance. So that's the classic assumptions. It's not really valid in many cases. That's really the case where, for example, in many of the competitions or even research problems, you look at your data, you will actually find that you probably want to partition your data into different subparts and learn different model for different subparts, simply because of a lot of reasons. I mean, maybe in certain subparts, there's not enough supervision, and in some subparts, there is plenty of supervision, so even a simple model should learn pretty well, and so on and so forth, okay? Yeah, the traditional assumption is that everything comes from the same unknown distribution in an ideal fashion. So the input of the classification typically is actually it looks like a relation table. Basically, let's say this is our x1, x2, xn. So this could be our document 1, document 2, converted to x2, and so on and so forth. So the number of rows is number of instances, and the number of columns are actually features. Feature 1, feature 2, up to feature, let's say, v. If each feature is, let's say, how many times this document, for example, the number here is 7, means the first document contains the second word 7 times. Okay? So usually you are looking at this kind of table. So that's why the pandas is actually a very handy way for you to manipulate tables and do some kind of calculation. And that's why it's very handy. And we usually assume that the last column is actually the class attribute. So again, we usually use binary classification to say, okay, this is 1 or -1, -1, 1, and so on and so forth. Okay. So the number of attributes is usually number of features plus 1. Usually the last one is the class attribute. And we usually split the data into different subsets and then do different kind of learning. Okay, so if we split into 3 parts, we actually have the training data and the testing data first. So training data is actually trying to build a model, and testing data try to evaluate how well the model works. Okay, you don't want to build a car or invent some kind of medication, right? And without knowing what's the side effect, or having a car, you don't know, how fast it can drive, how safe it is. And without any test, you just push to the market, right? It's impossible. So basically, what we do is that we look at the error, okay? Or 1 minus error is the accuracy. So there are different kind of, basically they are equivalent. So the training error is actually 1.0 minus the correctly labeled the number of examples in the training data set, such that they are correctly classified versus all the training examples. Okay, so if you feed in 100 training examples and the model only makes 3 errors, basically your error rate is 3%. Okay, but for some reason it turns out that we cannot really use training error, rely too much on training error. Why? Because in most of the method, they actually can go through training. I mean, they at least go through each and every training example. I mean, or with high probability, and sometimes they go through several times, and while adjusting the model. So it's almost like in real life, if you have already studied the final exam paper, then take the final exam again, right? So the performance you have is not really reliable. So the best way you actually can test how good your model is to test it on another set of data that you never ever have seen before. Okay, so these are actually the test data, and also you have the correct label for each and every one of them. And then you can do the same evaluation. You can actually get something called test error, or sometimes we call it generalization error. And that's exact error that we really care about. Okay, because just like exam, I mean, I mean, you need to be able to, if you think you are learning very well, you should be able to solve problem you have never seen before, right? That's the best way to test whether you really learn the key part or just memorizing, how to solve a problem that you already seen before and know the answer. Okay, and usually you also need to split some kind of data, which is called development data or validation data, just in case you have some parameters to tune and several models to choose from and so on and so forth. So that's the typical kind of data set you have. So we quickly do an overview. So let's look at this sort of like close to real examples where, let's say, you have a database or data set or Excel file with all the employees. So you can see that the attributes are typical database attributes. EID is employee ID, name, title, employee date, employment date, and on which check. So again, this is, we are trying to use Australian academic things. So if you look at the attribute, the raw data, so here it looks like it's already close to a vector. So here we have 1, 2, 3, 4, 5, 6, 7 instances, right? And it looks like we already have features, right? It's already in a tabular format. But we really need to look at, okay, I need to say that we want to predict whether, we want to predict whether, actually I forgot what's the, tenured or not. So again, here in Australia, we don't call it tenured, it's called continuous or contract. So in university, you sign up either a continuous job position or contract job position. Okay, so these are the raw data. Okay, you want to build a model to do the prediction. So the first thing you do is that you need to recognize this is the raw data, although this is already easier than text or image, which we so far probably have no idea how to convert into numerical vectors. We actually need to do some kind of pre-processing so that we can actually obtain the training data. So let's look at the columns. So features. For example, we can think about the EID as a feature, employee ID as a feature, right? Do you think employee ID will be good to predict whether the corresponding employee will actually be tenured or not? Probably not, right? Because if you know database, or in many cases, I mean, just like your student ID, okay? Unless you believe that a particular number actually bring luck to you, right? Otherwise, I don't think there is any strong correlation between any of the features on the student ID with your grade or whatever. So the same thing can be said at EID. In database, I mean, typically you have auto-incremental or serial whatever field where they randomly give you a non-repeating number, okay? So even if this data is available, it doesn't mean that we actually need to preserve it. So you can think about that this is our object. Our object is a tuple, and we need to extract features. So if we decide EID is most likely, by our prior knowledge, it's not going to have anything to do with the task we are going to do, we can actually drop it entirely, okay? Then we look at name. Do you think name will actually have anything to do with whether you will have a tenure or not? No, right? Anybody says yes? Yeah. Okay, so that's what I want you to think carefully. Although we know name itself has nothing to do with, I mean, most like, I don't think, again, by the same token, I don't think any particular name will actually have a good correlation with the class label. But from name, especially for this kind of things, I think we can reasonably extract gender. And maybe there are some kind of implicit gender imbalance or discrimination, whatever. I mean, I'm not saying that there are, but you can extract some kind of data. So basically, what you can do is that you can write a feature function given a name, right? It actually gives you male or female or unknown, right? Let's say. Because if I give you a, let's say, Chinese name, because of the it all spelled by the sound, pronunciation, it's very hard for you to figure out whether this is male or female. But basically, you can convert. So basically, we do have these kind of things in the original data, but we really convert it into, let's say we forget about the unknown, male or female, right? So the same thing can be said about title. So you can see that even for the professor, you have professor and the science professor. So that's unique in UNSW. So yeah, and I reckon in different universities, they might have different whatever titles. But so here we actually can take these kind of titles as if they are categorical attributes. Okay, so we have at least 1, 2, 3, 4, 5. We have 5 different titles, right? But if you do have the domain knowledge or you have the choice to do some kind of pre-processing, you can say, okay, professor and the science professor, they are all professors. So, so basically, you can convert them into the same thing. And also, I can say a lot of things about employee data and the track and so on and so forth. So the message I want to say is that this kind of feature extraction process is actually very important, and it really depends on your knowledge, and it's actually an evolving process. For example, if you read a little bit more about the academic system in here, in Australia, you probably will actually figure out something else. But if you are new to, let's say, for example, the similar knowledge we actually just talked about probably don't work in another country, right? Because they might have some other strange academic systems. But without further ado, let's say we do this kind of extraction. So first of all, from name, we extract gender. From the title, we extract rank. Okay, and here we only have 3 rank. So even if there are many different titles, if you look at our university, there are many different kind of titles, but we actually all categorize them into 3 different levels. And from the employment date, we actually can extract year. Okay? In theory, you can extract a month, right? How many months you have worked in here, or how many days, or even how many minutes you worked in UNSW, right? Okay, so again, if you know some background, you probably know that a year is a good choice between how much information you have and how messy it becomes, okay? Because every information, you can get from year actually can be get from minutes, right? You can say how many minutes you worked in the university, but probably it's much less transparent or sensible for ordinary people to figure out, right? And finally, we need to convert the track into the class labels, so and no and the yes and so on and so forth. So once we have the training data set, we actually can do some kind of model learning. So so these are the training data set, and we can have some kind of classification algorithm or classification model, and usually it's actually parameterized by some kind of parameter theta. So theta again usually is a vector, and we can store the model on the disk. So one of the simplest model is actually the decision tree kind of model. So it's like a rule based. So if the rank equal to professor or year greater than 6, then tenure equal years. So if that's your model, that's almost like a one-line model. Your parameter is this predicates and this predicates, right? In theory, also this or. You can use different kind of logical combinations. So this is actually, you can actually come up with different kind of predicates. So in this case, you can think about rank equal to, there are 3 predicates on rank. There are several predicates on year. There are several predicates on gender, 2 predicates on gender, right? Each of them can be plugged in here to become a model. But they will actually have different performances. Okay? So it's our job to select a good model to use. Okay, so if you apply the model on this data set, you will see that the predicted results will be something like this. So if another symbol we typically see is that the ground truth we actually call it y, and this one we actually call it y hat. So the hat usually in statistics it means the estimated value. Okay, so then we can actually see the corresponding y and the y hat are the same or not. Okay. So you can see that the training error is 1/3. You can see the last 2, the prediction is wrong. Okay. Then if we really want to evaluate how well the model is, we cannot do this on the training data set. Okay, and to make it very simple, there are actually models where you can make sure that the model have 100% accuracy or 0% error on the training data set, but typically it's not the case on the testing data set. So you need to present it with new examples you have never seen. So for example, you give it another object and do the same transformation, feature extraction. You have male, Jeff, professor 4, and you know the ground truth label, yes. Okay, and you run the model, and the testing error is 50%. Okay, these are all hypothetical examples, but the trend is actually very common. So you usually will see that the testing error is going to be higher than the training error of the same model. It's very reasonable, right? I mean, if you have already trained on a set of questions, and then I give you the question to test how well you did, versus I give you some new question to test, of course, I mean, you are likely to do less well on new questions, right? So, so this is very reasonable. And in fact, we don't, I mean, an ideal model is that we want to minimize the testing error, and later we'll also talk about the overfitting. We really want the testing error and the training error not to be too different, okay? But we will talk about this in the overfitting part. And finally, if we decide that this is the model we are going to use, we can deploy it on the real unseen data. So these are the data where we don't really know what's the class label, and we can only rely on our model trying to do the prediction. Okay, so in this case, it will actually be yes. Okay, so that's the general idea. So the next thing we quickly talk about, these are all the concept things, is, as I emphasized, what we really care about is the testing error or generalization error. We usually say that we want a model to generalize to new or unseen data. This is actually very important. Okay, so in practice, because of typically many algorithms have a lot of parameters to choose, we actually need to choose the best one out of a bunch of them. What we can do is that we can evaluate the naive idea that we do have testing data set. These are data sets that we kept away from the training, right? And if we do have, let's say, 10 different models, we can actually use, ask them to do the prediction on the testing, and on the same testing data set, and see which one performs the best. Okay? But the problem is that if you pre-split training and testing, there is a danger that maybe the model is pretty good, but it just doesn't work on some examples in the testing, right? A more reliable way to do that is that we actually do something called K-fold cross-validation. So usually it's called a CV, cross-validation. Okay? The general idea is that if you really have this kind of training data set, okay, you chop down into K pieces, or K partitions. So here, K typically is 5 or 10, whatever. These are the numbers that are widely used. What you do is that once you chop them into, let's say, 10 pieces, every time you reserve one piece as the real test data, and use the 9 partitions to do the training. And then you iterate over all the possible choice of testing partitions. Okay? So for the same model, again, you use the same model, but you train the same model with the same parameter 10 times, right? And each time you actually get an error, E1, E2, up to E10. Then finally, you just do the average. That will actually be a more reliable and a robust estimation of the real training, the real testing error or generalization error of your model. And you can actually do the selection based on this number. This will actually be much more reliable than if you only fix one portion of the test data as the one portion of the available ground truth data as the test data. That will actually be less robust. Okay, and also you can see that under this kind of cross validation, every point or every data in the training data set is actually used once as the testing, and then you do the average. So in some sense, you really get, you actually achieve, this is sounds almost like cheating. So you actually used all the data to do the training, although it's not in the same batch, but basically you also use all the data to do the testing, right? So, and the final error you get is actually almost like, in some sense, the average error for the same model on all the data.
And our models are all the same for all of this?
Yeah. Yeah, whenever you do cross-validation, you actually apply the same model with the same theta on, you just treat these as 10 different problems. And learn the model and then do the prediction.
What's the difference from just mashing all of them together in one file and training and testing your...
Yeah, the problem is that in order to reliably test the performance of data, you need to fix the testing data, right? So if you prefix your testing data, there is a danger that a particular model just accidentally works very well on this portion of data. For example, your testing data is only 10%. You don't want to say, so if you get your heads around, you can think about the final method, the final error you get from this cross-validation is in some sense more like the average error this model will get on if you treat every point as a testing data set. Because otherwise, for example, if I shield them off, you only fixedly use this one as a testing data set. You are only using 10% of the data as the testing. It's very hard to argue that your model, of course, you can linearly scale up, or you say this 10% is represented points of my training set. But again, this is very hard to argue. But if you do this kind of cross-validation, then it's much easier to sort of argue that you actually get some kind of average performance on unseen data, because whenever you do the prediction on every data, it's actually haven't seen it. Okay. Okay. So that's the most of the important concepts I want to quickly cover. So I think I need to quickly move on to the logistic regression part, because so one thing that next week I'm going to have a conference trip, so I'm not here, but I will get Dr. Sun to teach the decision tree and the naive Bayes here. So I'll see if I can finish this one. Otherwise, I'll resume from after I come back from the conference. Okay, so let's start with, so again, because of this kind of arrangement, in theory, I should talk about decision tree and naive Bayes because these are actually much simpler model. But we have to start with a reasonably simple model, but it has some kind of math behind it. So let's see how it works. So don't worry about these kind of things. Probably I will come back later after we talk about Bayes. For example, the naive Bayes model actually belongs to the kind of generative models, and the model we are going to talk about is called the logistic regression, belong to discriminative models. Okay, so these are the some big differences in terms of the philosophy they look at the task. So as I said before, many of the classification problems essentially are trying to solve a regression problem, and we actually spend some time to look at the regression. So in regression, I think anybody who have ever done some kind of physical experiment will actually will see this kind of things where the physical law actually predict that y, the outcome, is going to be a linear, are going to be linearly correlated with your input x. But when you do the experiment, the data point you get is not exactly on the linear line, right? So you actually use some kind of least square linear regression. They are actually built-in software. So if you have the standard calculator, they actually build that kind of things into the calculator as well. So so you can see that it's actually very important and in a practical way, especially for engineers. So let's look at what it does. Okay, so again, we look at a very simple example where x is one dimension and y is one dimension. Okay, we try to do this on this kind of geometrical notations, but we can then see that if you use matrix or vectors, you can generalize easily to any arbitrary dimensions and also give you some additional benefits. So we are dealing with x and y, so these are scalar values, but we actually pre-process the data such that we map x into something called homogeneous coordinates. So for each of the x, it's one. So you can see this is a scalar value, so it's not in bold. I actually convert it into a vector. And it's two-dimensional vector because this is the original scalar value. And I actually use 1. I just append 1 to any of the values. Okay? And why we do something like this? Because the linear line we are going to learn, if we don't do this, is almost like ax plus b, right? Something like this. So I can write this one as ax plus b times 1, right? That's the same. And if you know, this is actually our inner product. Again, this is actually this is our AB transpose. Actually, if you know the inner product, we don't need a transpose. It's actually x1, right? So the inner product is nothing but AB transpose times x1. So inner product is essentially you get the corresponding one, you do the multiplication, and sum up all the corresponding multiplication results, and you get something like this. Okay, so again, here I actually put 1 afterwards, but essentially if you switch the order, it's the same thing. So the good thing about using this kind of expansion, if you like, is that now we don't need to worry about this term. This term is usually called the bias term. Again, the choice here is really like just to simplify the formula. In fact, when we do the SVM, basically this bias term is explicitly preserved because it's in that case, in their model, if we separate the b term out, it's actually easier to do the math. So again, it's not always the case that you need to expand into the homogeneous coordinate system. So no matter which line we have, so that's why this A and B, essentially we actually call it a W. So it's again, yeah. So we try to find the best vector W consists of this W0 is actually going to be the B we wrote before, and W1 is going to be a coefficient together with the input X. We want to find the best W that explains the observed Xi and Yi, right? That's our goal. So before we can actually define the problem, we need to know what does this best mean. Okay? So intuitively, let me see if I can, yeah, I can. So I deliberately use, this is my X4, Y4, okay? If I deliberately use a large value, okay? And if we consider this line, its prediction for the X4 will actually be this point. Okay? The observed point is this one. So this is our predicted Y point. This is our Y. Again, I don't use the subscript to say this is the false observation, but the key point is that you get the estimated Y by the model. So the estimated Y is actually parameterized by this particular W. So given a W, you actually say, okay, given the same X4, what's the most likely, what's the predicted Y, right? And you do have a fixed observed Y. So you need to quantify what's the cost, or what's the difference, okay? So one simple way, I think everybody agrees, is that if I remove these kind of things, is to look at the difference called epsilon I between the real value and the predicted value. Okay? So this is actually the method that we are going to use. So we actually think these are the arrows. This is the predicted value, and this is the, so there are hats here. So it's model predict value minus the real value. And because this epsilon could be positive or negative, so we do want to sum them together, but we don't want the arrow to cancel each other off. So that's why we do the square. So this is very similar to the SSE we talk about in the optimal binning. So everything, you can see the same idea comes up again. Okay? So again here, that's also called the least square fit, because our sort of like arrow function or cost function is the least square fit. It's possible that our arrow function is, this loss function is going to be epsilon I, take the absolute value. If we do something like this, this is going to be something called a robust linear regression. Okay, I won't talk too much about this, but the general idea that to highlight that many of things actually can be customized. Okay, of course, some of the object function mathematically or numerically will be easier to solve or whatever, but you really have the freedom to, once you understand what the model trying to do, you can customize it to your own scenario. So with all these kind of things defined, then we actually have a defined problem. So we can find W such that this corresponding loss over all the observed data is minimized. Okay? So how to minimize a function? So this loss is going to be a function of this W, essentially. The function will be very complex, like 1 to n. This is like W transpose xi. Again, I think in my notation, I is in the superscript. Xi minus the yi, and so basically the function is going to be fairly complex, but it doesn't matter. We can actually say that the only variable is W. The only variable is W. Okay, so that's why I can write in the form of FW. And we want to find the W such that FW is minimized. Okay, so then this becomes a very simple function minimization problem. And there are actually a lot of ways to do that. So I won't go into details, but you probably know that if we want to find a minimal point, I need to make sure that this f, first derivative of this f at the particular point is going to be 0. So essentially that's the condition for local minimum. Okay, and although I use the Taylor theory in one-dimensional case, the whole thing still works on high-dimensional case. Although the condition become, I think it's a necessary condition. So even if you have X star which satisfy these kind of conditions, let me see. Yeah, I think it's not necessarily the local minimum, but anyway, it could be a saddle point or something like that. But essentially, you still test the first derivative to be equal to 0. Okay, so that's the key message. I won't go through the derivation. The derivation is actually in this slide. Yeah, the reason I actually use this one is that you will see that later in the algorithm, in the SGD, we actually use just first derivative information. And in some kind of more advanced algorithms, they can actually use the second order derivative information. Okay? And if you use second order, it's very similar to the Newton's method you already implemented in the lab. Okay? So we won't go into that, but just to tell you that how to use the second order derivative. So it's everything here. Okay? So what we do is that we need to take the derivative with respect to W. Okay? In theory, effectively here we actually take, because W is a vector. W consists of W0 and W1. Okay? So we actually take derivative with respect to each dimension or each component of W. Okay? And if we don't do that, we actually directly, so if we actually do something like this, we do partial L to partial W0, partial L, partial W1. So you do the partial derivative for each component and put them into a vector. This gives you the gradient. Okay, so basically we can say you take the gradient of function, which give you a vector. If the input, if the variable you do the gradient is actually a vector, the output will be a vector. So here we actually do it just individually. If you are not familiar, just do it individually. So it's everything here is the normal calculus. The only thing here which involves some kind of vector format is this one. Okay, so this one, the simplest way is to expand into the components. So this is nothing but an inner product. So W transpose X is essentially inner product between W and the Xi. So if you expand it, it will become, let's say, if of sum of Wi, Wj, I use J is already used, let's say Wt, and Xit. Okay? So you are actually, because you are doing this kind of partial derivative to a sum of terms, essentially you can move this inside, right? And we know that if you do the partial derivative of Wj, if t does not equal to j, it doesn't matter. It's almost like if you have y equal to ax1 plus ax2, right? If you do the partial derivative of x1, you treat x2 as a constant, right? Although you can actually do partial y of partial x2. Okay, whenever you do this one, you treat only x1 as variable and everything else as a constant. So you can convince yourself that if you do something like this, only t equal to j matters. And when t equal to j, the corresponding one is this one. Okay, so there are some kind of mathematical derivation, but just to show you that we, if in doubt, you just expand to the scalar value version, and you can actually do it. So after doing this, you actually get something like this, and you replace this one, you actually get this one. Okay, so so this means the optimal W need to satisfy this kind of condition, and I can actually that's the partial derivative to each and every dimension of W, and they must all equal to 0, right? This is the condition for finding the minimal, and this means for every j, because this is this guy minus this guy times this guy, go to summation, so 2 doesn't matter because it's equal to 0. So essentially it's this term and this term should be equal. And this is something I really want you to remember. This is actually an important property of the model. And although this is for linear regression, it carries over to logistic regression and to many other models as well. Actually, you can generalize to generalized linear model. So all the, let's say, exponential family functions actually all satisfy these kind of things. So if you think about the symbol, so this is actually a column vector. Because I is the variable, j is, so I think in the next slides when we talk about examples, it's easier. But j is a column vector. This is also a column vector. Now the only thing that this summation is actually doing, this is actually doing an inner product. Whenever you see summation of two things multiplied together, it reminds you of inner product, right? So basically it's your y, again this is y estimate, and your, let's say this is your x, you take the j's column, this is your xj. So you take these two vectors and do the inner product. And this should be the same as the real y. This is y is the real y, inner product with the same column. Okay? So that's what I said. Okay. So the model prediction, the predictor model is going to, if you look at all the instances, it's going to be a vector. And the vector dot product or inner product with any of the columns in your data matrix X should be the same as the real Y doing the inner product with the corresponding X. Okay, that's the constraint the model needs to satisfy. And once you satisfy these kind of things, the corresponding W will actually be the optimal one. So let's look at the real examples. I skip this one. So look at this example. So I take some examples. So this is your X data matrix. So each row is, so again, the first column is actually useless, sort of like useless. It's always 1. And this is your estimated Y. This is your real Y. Okay? So the previous condition says, okay, if I take this one and I take the first column of X, I do the inner product. Then my model prediction for each instance, inner product with this one, these two values should be the same. Similarly, if I take this guy, inner product with this guy, and I take this guy and the inner product with this guy, these two values are going to be the same. Okay, so if you just, I don't have the example here, but essentially if you write down the whole thing, once you know the vector format, essentially you write out, because each y1 estimation is going to be w times this vector. So basically you write down two constraints and solve the equations, and you actually can get the W0 and the W1. Okay, so but you avoid all the dirty mathematics, because otherwise, I mean, you can list all the equations and you plug into the previous whatever this kind of formula, and also you can do the minimization just without using the vector. But using vector actually give you a much more clear picture, and this kind of picture transfer to the much more complex models. Okay. Okay. So what if our X is not one dimension? So you want to say my model is Y equal to AX1 plus BX2 plus actually alpha1 A2 X2 A3 X3 plus some A0. Okay, I can try to find a linear relationship between multiple X with the corresponding Y. So if you use the vector notation, it's almost the same thing, because essentially all you need to do is to write, this is my X, so this is my, so basically this is my first, so this subscript means the first point, if you like. This is the first, this is my first point, and this is my first dimension, and this should be x2, 1, and so on and so forth. Okay? And the corresponding AI is going to be this W. So if you use X times W, essentially if you time this one with this one, to give you this one. Right? So the idea is that this easily generalizes to more than one dimension. Okay, you don't even need to do anything. And also, by the same token, you realize that the best estimated Y satisfies the same condition. So if you just pour out this column and do the inner product with the real Y, and you pour this column do the inner product with the estimated Y, that should be the same. Okay, so this naturally extends to multiple dimensions. And also a side effect is that what if I want to do something like y equal to ax squared plus bx plus c, right? I know that, for example, that's the distance traveled, whatever, if you have acceleration, right? So basically, I know my model should be a polynomial of degree 2. So how do I do the least square fit? So again, you can plug in the the function and do the minimization all over again. But essentially, you can see that if I basically it's something like this. So the polynomial you are going to do is nothing but x raised to the power of m, right? And then you have a corresponding Wm, x raised to the power of 2, and I have W2. Okay? So in other words, you can actually still use this multidimensional linear regression, but for each of the things, you actually use the corresponding x in this time. So basically, if you know what I'm talking about, basically if your x is actually 1, 2, 3, 4, right? You expand it to another x prime, which is actually 1, 1, 1, 1. This is 1, 2, 3, 4. This is actually your square. So this is 1, 4, 9, 16. Cubic, if you like. This is 8, 27, 64. Okay, you can do something like this. Okay, and then everything is still the same. Okay, so this probably is pretty quick, but I think you probably get the idea that, yeah.
So I don't need to recalculate the derivatives before that came from linear.
Basically, that's the messy calculation, but after calculation, it is simplified to a very simple equation.
Well, no, but doing that transformation that you just talked about, because we derived it from a plus b times x, right?
I derive from okay, but if you look at my derivation, there is nothing that I specify how many dimension x is, because essentially if you think about it, I just do a generic. When I use examples, I try to just limit myself to a simple case. But if you look at all the derivation, I don't rely on the fact that x is 1 dimension or 2 dimension. I just do the partial derivative to every dimension of x. So that's the key. So it works naturally, generalized to any dimensionality. Okay. So let me get through this idea because it's related to the something like KDE, which is mentioned. Okay, so the previous one actually I tried to give you a linear algebra interpretation of what's the best W. Okay, I derived some condition that the best W must satisfy a set of equations, and then I mean you'd better just use this example and do the calculation by yourself, and you can feel what does it give you. Okay. There is another important interpretation I call the probabilistic interpretation. The high-level idea is that, first of all, I can use any W, okay? Because if I really give you a few points, right, you can say that the true line could be something like this, right? Okay? But I can also say this W should be this one, because if you look at the slope of the lines, so we just need to figure out, okay, which one is, so as I said, I mean, any W is possible, okay? It's almost like if you claim your accuracy of shooting the target is 90%, but I shoot only twice, and I didn't hit any of them, right? But this is still possible, but it's just not very likely. If you are, for example, if I shoot 10 times, and I only landed one shot, right? And I still claim that my accuracy is 90%. It's still possible, but it's very, very unlikely. Okay? So we actually want to find the W which is most likely. So this is actually the MLE, the maximum data likelihood thing. Okay? So I won't go into detail because essentially the logistic regression will actually do the same thing. But I just want you to look at this point of view. And for this kind of probabilistic interpretation, the key point is to understand how to derive this one. As I said, I mean, this is my y, this is my real y, and I can have, for the same x, okay, for the same x, this is my estimate, which is conditioned on W, a particular W. So if you use W, different W, this y will actually goes up or goes down. Okay? So in order to quantify the probability, essentially I need to quantify this term. So if I know if my model prediction is actually yi, what's the probability that I will see the observed value up there, right? Okay, so if you think about, you can plug in different kind of models. Okay, and if you don't have any idea, you can think about, okay, my intuition that if my W is good, right, if my W predict, okay, my prediction is something like this. If Y and the Y estimation is very close to each other, the probability should be high. Right? For example, if I claim my accuracy is 90%, if I shoot 100 times, right, you do expect the number of times I hit the target is around 90, right? Because that's my expectation. So if I really landed 92 shots, then it's highly likely. But it's very unlikely that I will land 15 shots out of 100 trials, right? So basically, you can think about the simple way is that you say, okay, the probability is proportional to some kind of distance between yi and y estimate of I. Okay? And depending on which kind of distance you use, this corresponds to different kind of probabilistic interpretation. In specific, if you use the L2 distance, it gives you the Gaussian prior. Okay? But anyway, no matter which model you actually feed in, it's going to be a parameter of the W. Because if I use different W, this model estimation will be different, and hence you will end up with a different value. So this is going to be a different value for W. Okay? So if we assume the ID assumption, the probability of seeing the whole data set is something like this. Because you go through all the observations, you vary I, each one you actually get this thing. Then this is the MLE. So we choose the W such that this whole function is maximized. Okay, I won't go through the details, but basically you do the derivative and equal to 0, and you can actually find the result. Or, as I said, we can incorporate some kind of prior. Yeah, we won't talk about this too much, but once we learn the Bayes perspective, you will actually understand that we can actually say, I prefer my W to be close to 0 or whatever, so that's my prior. Okay? And later you will see that this is only for linear regression, and this view is very handy in the sense that when we go to logistic regression, the only thing that changes is this one. So you can think about it, you probably can derive the very similar model by yourself, because essentially in logistic regression or in classification, this thing is going to be either 0 or 1. It's not going to be a real value. Okay? And my model estimation is going to be a value between 0 and 1. So you need to impose some kind of probability estimation there. Okay? And in that case,